This is 1998, question 6. Okay, so 1998, question 6, and what we're saying is to find simple harmonic motion. The motion of a particle is simple harmonic motion if its acceleration towards a particular point is proportional to its displacement from that point, and the acceleration is in the opposite direction to the displacement. So also direction is in opposite direction to displacement. The distance x of a particle from a fixed point O is given by the formula x equals 7 sine omega t plus 24 cos omega t, where w is a constant. Show that the particle is describing simple harmonic motion about O. Well, what we have to do is we have to differentiate twice, because if x is distance, the first derivative is velocity, and the second derivative therefore will be acceleration. So differentiate, and what we have here is sine turns directly into cos wt, the 7 goes directly down, differentiate the angle with respect to t, and we get w, 7 omega cos omega t. Next one, the cos turns directly into a minus sine wt. The 24 travels down undisturbed, differentiate the angle, and we get w. And that's going to get me 7 omega cos omega t minus 24 omega sine omega t. Differentiate a second time. And we differentiate a second time, we get the acceleration. Acceleration. Now this time we're looking at a product rule, aren't we? U and V. So du, what's it, du dt? Actually no, it's constant. It's not a product rule because omega is not a variable in this question. So it's going to be 7w travels down unaffected. The cos turns into minus sine omega t. Differentiate the omega, and it comes out, omega t, you have to differentiate the angle, minus 24 omega travels down unaffected, sine wt changes into plus cos wt, differentiate the angle, omega. Let's find out what's going on here. It's going to be, these are being multiplied by each other, by the way, sorry, I've written down slightly wrong, okay? So it's going to be 7 omega squared minus 7 sine omega squared wt minus 24 omega squared cos wt. Factorize out omega squared minus omega squared sine wt plus 24 cos wt. And what does this equal here? This part here is the original x. Acceleration equals minus w squared x. Okay, and then what you can see is therefore undergoes SHM about x equals 0. Therefore SHM about x equals 0. Okay. Calculate the amplitude of the motion. How do you find amplitude? Can anybody tell me?
Change the first thing, what do you stand for? It moves in two forms. It moves in x and y.
It moves in two different forms because of the two components. Okay? The two components make it. It usually be one component only, but it has two different components. Because it has two different components, you're going to have to get the magnitude of the two different components. Okay? And they both have maximums. When do they both have a maximum? They both have a maximum of. Get the amplitudes. I'm going to get the amplitudes of both individual parts. Okay, so look, if you were to say 7 sine wt, and what's it, plus 24 cos wt, technically speaking, 7 and 24 are the two at different amplitudes of the two different components. And then what happens next is we're going to get the quadratic, we're going to do Pythagoras' theorem, 7 and 24, square them up, so it's going to be the square root of 7 squared plus 24 squared, and what's that?
Yes, 25.
25. So the amplitude of the full thing is 25. Long story short, if you're ever given a question whose motion is the sum of two different equations, to get the resultant amplitude, use Pythagoras' theorem of the amplitude of each of the individual ones. Is that right? So, now we're on to part B. An elastic string of natural length 1 meter is extended to 20 centimeters. Now, 1 meter, 20 centimeters. Let's change these to 0.2. Let's change that one to 0.4. But a particle attached to its end and hanging freely. The particle is then pulled down a further distance of 0.4 meters and then released. Show that the particle moves with simple harmonic motion when the string is taut. Find the height of the particle above the equilibrium position in which the particle will rise. Okay guys, we're going very similar to the question we did earlier. We're just going to draw our wall, then we're going to draw our natural length. What's our natural length? 1 meter. And then it is extended 20 centimeters by a particle attached to its end and hanging freely. Hanging freely means what? Equilibrium. It's equilibrium then. This is the point at which you no longer have tension, and this is the point of equilibrium where the tension equals the weight. Okay? And we don't know the weight of the particle, so it's going to be mg. Now, what happens next is we then go in here and we end up extending it further. So this part here is gone, and then we extend it by how much? Power is then pulled down a further 0.4 centimeters, okay? So it'll be this one here, we'll just colour it in red. So a further 0.4 down to here, and now mg is down here. Okay, now what we're going to do is we're going to find the equilibrium position, okay? So, show that when the particle moves with simple harmonic motion, the string is taut. Okay. So what I'd like to do is I'd like to find the elastic constant first. So at equilibrium, tension equals weight, T equals mg. Okay, and what is at equilibrium the tension equals the weight, K times the extension equals mg. Now what is the extension, guys? Extension is 0.2 meters. K therefore is when you divide 1 by 0.2 you get 5. K equals 5 mg. The equilibrium constant is 5 mg. Okay, so that's handy information there. Okay, then we move this up. Now that we've used our equilibrium position, we now should go to the displaced position, which is part 2. Okay, so this is the displaced position. Now, in the displaced position, okay, okay, so the displaced position, okay, F equals mg going downwards, okay, minus the force going upwards. Now, it's going to be K times the entire extension. What's the entire extension? The entire extension is going to be your 0.2 plus x. So it's going to be K times 0.2 plus x. And what's K again? minus 5mg. Minus 5mg. Okay, so F therefore equals, it's going to be mg minus mg minus 5mgx. Now remember, the tension is bigger than the weight because you pulled it down past its equilibrium position. Tension is going to be bigger. That's why we're expecting a negative number again. F equals minus 5mg x. Okay. Now, what is the weight again? Oh, force equals ma, which is minus 5mgx. And then m's will cancel. We can figure out what g is. G is 9.8. 9.8 multiplied by 5 minus 49x. A equals minus omega squared x. Omega equals 7. Okay. Next one after that. Find the height the particle will rise above the equilibrium position to which the particle will rise. Okay, so W equals 7. We just need to remember that. Now, what I can do here, guys, remember what we learned from the last question. We can use the cos function to just get us right to the other end right away. So look, I'm going to find out from here to here. I'm going to find out this position, start here, and I'm going to end here. You happy enough with that? I'm going to start here and end here. That's going to tell me the point at which the tension stops working. So what I'm going to do is going to use the cos function. What is the cos function again? X equals A cos WT. Okay, now look at this. X is going to equal what? X is going to equal minus 0.2. What's its amplitude, guys? What do we say X is? Do we know what X is? Huh?
Oh, it's 0.4.
Sorry, A is 0.4, isn't it? Because you pulled it down 0.4. So 0.4 cos 7t, right? Minus a half equals cos 7t. Cos inverse a half, what do we get? It's going to be pi minus the reference angle. The reference angle is cos inverse plus a half. Huh?
Pi over 3.
So pi minus pi over 3, which is?
No, it's reached pi minus 2 pi over 3. The answer you get is pi over 3. I think that's the one.
So what we get for this angle is that we're going to get that 7t equals pi 2 pi over 3. T equals, what's going to be 2 pi over? 2 pi over 21, right? 2 pi over 21. Now, and do you know the funny thing is, I didn't need to find that even, because I was going to put that into a velocity equation, but actually, as it turns out, you didn't actually need that. That's actually the time it takes for the string to become taut, but what we actually realistically should have used was actually the phi equation, which would be phi squared equals w into the square root of, w squared a squared minus x squared, and this is what we should have used. Actually, we should have used phi squared equals 7 squared, what's it, times 0.4 squared. Now minus 0.2 squared, because it's on out the other side. So we're going to get phi squared equals 49 multiplied by, what's 0.4 squared minus 0.2 squared? Is it 0.12?
Yeah.
And 49 times 0.12 and square root it?
Root 0.6g.
Root point?
6g.
Which is it 2.43?
Yeah.
2.43, right? And then at this point in time, when it reaches the end, its velocity is going 2.43. Insert that into phi squared equals u squared minus 2as. And what happens then? 0 equals u squared, which is 7 squared is 49, plus 2 times, what's the acceleration? Gravity's working against it now, isn't it? Because it's travelling on its way up, there's no more tension, and gravity's working against it. So minus 2 times minus 9.8 times S is what we're trying to figure out. And then we're going to get 19.6 S equals 49. S therefore is, what's S going to be?
S is 0.3.
Is that right?
And the add on 0.3.
0.3. Now, S is 0.3 meters. That means that it raises 0.3 meters from here to here. It's above equilibrium, which is 0.3 plus 2, which is 0.5. So the answer there is going to be 0.5. Okay, guys.